Okay, so today we're going to be diving into something pretty wild. This paper titled "No Prop, No Back Prop, No Forward Prop, No Problem." Catchy title, right?
Yeah, it really grabs your attention.
It really does, and it's really living up to that title, at least from what I've seen so far.
It's a pretty radical departure from how we typically think about deep learning.
Yeah, it's really questioning some of those fundamental assumptions that we've kind of taken for granted for years. But before we get too far into it, just to set the stage for our listeners who might not be as familiar with this area of research, can you just give us a quick recap of how backpropagation works, like the traditional approach to training neural networks?
Yeah, sure. So backpropagation, it's been kind of the workhorse of deep learning for decades, right? It's this iterative process where you feed data forward through the network and you get a prediction. Then you compare that prediction to the actual answer and see how wrong you were.
Right.
And based on that error, you calculate these gradients, these signals that tell you how to tweak the network's internal settings, the weights, to be a little less wrong the next time around.
Right, like nudging it in the right direction.
Exactly. It's like a feedback mechanism, right? The error signal is propagated back through the network layer by layer, and it adjusts those connections based on how much each part contributed to the overall error.
So it's figuring out which parts were most responsible for getting it wrong. That's like the credit assignment
Yeah,
problems.
exactly. Credit assignment, that's a key part of it.
Right, and it's that whole back and forth, right? The forward pass to make the prediction and then the backward pass to correct the errors. That's what allows these deep learning models to build those really impressive hierarchical representations that we see, right?
Absolutely. Those hierarchical representations, that's what gives deep learning its power. As you go deeper in the network, the simple features that were detected early on get combined into more and more complex features, like building blocks.
It's like the network is learning its own internal language, like a hierarchy of meaning, right?
Exactly. Yeah, it's building up this internal representation, a stack of increasingly abstract features that can capture these complex relationships in the data.
So that's backpropagation, the foundation of so much of what we see in AI today. But this paper, NoProp, is saying, hey, we can do away with all of that. No backpropagation, no forward propagation even. And they're still getting these neural networks to learn effectively.
It's pretty mind-blowing when you think about it, right? Like throwing out this fundamental mechanism that we've relied on for so long. And what's really interesting is where they draw their inspiration from.
Yeah, that's what caught my eye too. Tell me more about that.
So NoProp is actually borrowing ideas from areas like diffusion models and flow matching. These are techniques that have been making waves in generative AI, like creating realistic images and text and things like that.
Right.
And they're applying those ideas to this problem of training neural networks, but in a completely different way.
So how does it actually work? What's the basic idea behind NoProp?
Okay, so instead of having this end-to-end error correction that you have in backpropagation, where the error signal flows all the way back through the network, in NoProp, each layer is kind of on its own. It learns to take a noisy version of the target, like the correct answer, and just clean it up a bit.
So each layer is doing its own little denoising job independent of the other layers.
Exactly, yeah. Each layer has its own little denoising task.
So if each layer is working in isolation like that, I'm a little confused. How does the network as a whole learn to make sense of the data? Like doesn't it need those hierarchical features that we were talking about before?
That's a great question, and it gets to the heart of what makes NoProp so different. So the paper explicitly says that NoProp doesn't learn hierarchical representations in the traditional sense.
It doesn't. So then what is it learning?
So instead of learning how to transform the input data into increasingly complex features, the representation at each layer is actually fixed. It's just a predefined noised version of the target label.
Hold on. So each layer is working with a noisy version of the answer from the very beginning.
Yeah, that's right.
But how does that even work?
So each layer's job is to take that noisy label and the input data and then output a slightly less noisy version of the label. And then that less noisy label gets passed on to the next layer and so on.
Okay, so it's like a chain of denoising steps, with each layer getting closer and closer to the actual clean answer.
That's a great way to put it. And what's really surprising is that this approach actually works. They've shown that NoProp can achieve impressive accuracy on those standard image classification benchmarks like MES, CIFAR 10, CIFAR 100, the usual suspects.
Right? Those are like the gold standards.
Yeah,
So it's not just a theoretical curiosity, it's actually performing well on real-world tasks.
exactly. And not only that, it's also showing some really interesting advantages in terms of efficiency. Like it can be more computationally efficient compared to other methods that try to avoid backpropagation.
Okay, so this is starting to sound pretty revolutionary, but I think we need to dig a little deeper here, right? Like how does it actually work under the hood? What are the key mechanisms that make this no prop thing tick? And what are the implications of moving away from backpropagation? I mean, that's a big deal potentially, right?
Yeah, absolutely. It's definitely a paradigm shift. And to fully appreciate the innovation here, I think it helps to first understand why researchers have been so keen on finding alternatives to backpropagation in the first place.
Yeah, good point.
So backpropagation, as powerful as it is, it does have some inherent limitations.
Right, like what are some of the issues that researchers have been grappling with?
Well, one of the biggest ones, and the paper mentions this too, is that backpropagation is not very biologically plausible.
Meaning.
Well, it's not clear that our brains actually use this kind of synchronized forward and backward flow of information for learning. It's a very specific, very engineered solution that works really well for artificial neural networks. But
Right.
it doesn't necessarily reflect how biological learning happens.
So it's kind of like we stumbled upon this really clever trick, but it might not be the only way or even the best way to achieve intelligence.
Exactly.
Okay, so biological plausibility is one issue. What else?
Another big one is memory overhead. So backpropagation requires the network to store all the activations, all the intermediate values from each layer during the forward pass. And that's because it needs those values to calculate the gradients during the backward pass.
Right. So you need to keep track of all that information.
Yeah, and for really deep networks, especially when you're dealing with lots and lots of data like images or text, this can lead to a huge memory bottleneck. It limits the size and complexity of the models that you can train.
Okay, so memory is an issue. What else?
Then there's the problem of parallelization. So the way backpropagation works, the gradient calculation for each layer depends on the gradients from the layers that come after it.
Right.
So you have to do it sequentially. You can't really parallelize the process effectively. And that becomes a bottleneck when you're trying to train these models on really powerful hardware like GPUs, which are designed for parallel computation.
Right. It's like trying to fit a square peg into a round hole.
Exactly. Yeah. You're not fully utilizing the potential of the hardware. And then the paper also touches on some other potential issues like learning interference, where learning a new task can actually mess up the network performance on tasks that it's already learned.
Oh, wow. Like it's forgetting what it already knew.
Yeah, it's called catastrophic forgetting, and it's a big problem in deep learning, and backpropagation might be contributing to that, although it's still an open question.
Okay, so there are clearly some strong motivations for exploring different ways to train neural networks. And the paper does a good job of outlining some of the existing alternatives, right?
Yeah, they provide a good overview of some of the approaches that researchers have been trying. So you have things like gradient-free methods, which try to find better network parameters without explicitly calculating those gradients that we talked about.
Right.
But these methods often have trouble with efficiency, with accuracy, and with scaling to those really high-dimensional parameter spaces that you have in deep neural networks.
Okay, so they might work for smaller problems, but not so much for the really big complex models that we're interested in.
Yeah, that's the general idea.
And then there are things like zero order gradient methods, right? Which try to approximate the gradients by just sort of poking the network a little bit and seeing how it responds.
Yeah, you make small changes to the inputs or the parameters and then see how the output changes. But these methods can be really computationally expensive, especially for deep networks, because you need to do a lot of those evaluations to get a reliable estimate of the gradient.
So it's like you're trying to map out a really complex landscape by just taking a few measurements here and there, and
Exactly.
you might miss some really important details.
That's a good analogy.
Okay, and then you have these evolutionary strategies which are kind of inspired by natural selection, right? Like survival of the fittest.
Yeah, so they use a population of networks and they update the parameters of those networks based on how well they perform on a task. But these methods can be really computationally intensive. They need lots of data and lots of computation, and it can take a long time to get good results.
So they're powerful, but they're also kind of slow and resource hungry.
Right. Yeah, it's a trade-off.
And then finally, you have these methods that try to use local loss function, like difference target propagation and the forward algorithm, which we've talked about before on the show.
Yeah, those are some interesting approaches that try to decouple the layers of the network to some extent. So in difference target propagation, the idea is to learn the inverse mappings. so that each layer can generate its own target output independent of the other layers. And in the forward algorithm, you actually have two forward passes, one with a real label and one with a fake label. And you use those to kind of assess the goodness of each layer.
Right. So it's like you're giving the network two different perspectives on the data, and then you're seeing how well each layer aligns with those perspectives.
Exactly. Yeah.
But the paper points out that these methods also have some limitations, like difference target propagation. It relies on learning these really complex inverse mappings, which can be tricky. And forward, it might not always achieve the same level of performance as back propagation. So it's like there's this whole landscape of different approaches, but each one has its own strengths and weaknesses, its own trade-offs.
Yeah, it's a really active area of research. People are trying all sorts of different things to move beyond back propagation. And that's what makes NoProp so interesting because it's taking a completely different approach.
Right. It's not just another tweak on an existing method. It's really a fundamental rethinking of how we train these networks. So
Exactly.
so let's get back to that. How does no prop actually work? Like what's the secret sauce here?
So the key innovation is that NoProp reframes the learning problem entirely. Instead of trying to predict a target output directly, like you do in backpropagation, layer in NoProp learns to predict a cleaner version of a noisy target. And this is inspired by the success of denoising score matching, which has been really effective in generative models.
Okay, I'm starting to see the connection here. So it's like you're taking that idea of gradually cleaning up a noisy image or a noisy piece of text, and you're applying it to the process of training a neural network.
Exactly. That's a great way to think about it.
So during training, each layer receives the input data, like an image or a piece of text, and it also receives a corrupted version of the correct label.
Yeah, so you take the correct label and you add some noise to it, and that's what the layer gets to work with.
Okay, so it's like you're giving the layer a puzzle to solve, right?
Exactly. Yeah.
And the puzzle is to figure out what the original clean label was based on this noisy version.
That's a great analogy.
And the layer has to do this without knowing what the other layers are doing, right?
Exactly. Yeah.
It's working in isolation.
Right.
And here's the really mind-blowing part. The paper says that during training, there's no forward pass through the entire network at all.
Yeah, that's one of the key distinctions here. Each layer is trained completely independently, conditioned on the input data, but it's just focused on cleaning up its own little piece of the noisy label.
Okay, I'm gonna need you to walk me through this slowly because I'm having a little trouble wrapping my head around this. So if there's no forward pass during training, how how does the network actually make a prediction when you're actually using it?
Okay, so during inference, that's when you actually want the network to give you an answer. The process is sequential. You start with a noisy label at the input of the first layer, and this could just be random noise actually.
Okay.
And then that first layer, it takes the input data, like the image and that noisy label, and it outputs a slightly less noisy version of the label. And
Right.
then that less noisy label becomes the input for the next layer and so on down the chain.
Okay, so each layer is taking the output of the previous layer, which is a slightly cleaner version of the label, and it's cleaning it up even more.
Exactly. Yeah.
And this process continues until you reach the final layer, which outputs a label that's hopefully pretty close to the true label.
Right. And that's what you interpret as the network's prediction.
Okay, that makes sense. So the denoising happens sequentially during inference, but during training, each layer is trained in isolation.
Yeah, that's the key difference.
Okay, that's pretty wild. So now let's dive into some of the technical details here. The paper talks about these two probability distributions, P and Q.
Yeah, these are important concepts for understanding how NoProp works. So P is the generative process. It describes how the data, like the input image and the label, could have been generated. And it involves this sequence of latent variables, these hidden states that kind of represent the underlying process that produced the data.
Okay, so P is like the true underlying model of the data, but we don't actually know what it is.
Exactly. Yeah, it's the model that we're trying to approximate.
Right.
And then Q is the variational posterior. It's our attempt to approximate that true distribution P, and it's defined in a reverse manner. starting from a noisy version of the label and then working backwards to those initial latent variables.
Okay, so Q is like our best guess at what P might be.
Exactly, yeah.
And the paper then mentions that they fix Q to be a Gaussian distribution, this bell-shaped curve, using this thing called the variance-preserving Ornstein-Uhlenbeck process. What's that all about?
So that's a bit of a mouthful, but the basic idea is that by choosing this particular form for Q, they make the math a lot easier to work with.
Okay, so it's a mathematical convenience.
Yeah, it makes the optimization problem more tractable. The Ornstein-Uhlenbeck process, it's a well-studied stochastic process that has some nice properties that make it suitable for modeling how noise diffuses over time.
Okay, I'm going to trust you on the math here.
Yeah, no worries. It gets pretty deep.
And then the paper talks about the structure of P, the generative process, and they mention these weighted skip connections and a residual block. Those are terms that we hear a lot in deep learning.
Yeah, so the way P is structured is actually quite different from typical deep networks. So you have these skip connections that allow information to flow directly from the input to later stages in the process.
Okay, so it's not just a strict layer by layer hierarchy. There are these shortcuts.
Yeah, exactly.
And what about the residual block? What's its role?
So the residual block is where the actual denoising happens. It's a small neural network that takes the noisy label and the input data and tries to output a cleaner version of the label.
Okay, so it's like the workhorse of each layer.
Yeah, that's a good way to think about it.
And then there's this whole thing about optimizing the evidence lower bound, the ELBO.
Yeah, so the ELBO it's a key concept in variational inference. It's a lower bound on the likelihood of the data. And by maximizing the ELBO, we're essentially trying to make our approximation Q, that variational posterior, as close as possible to the true distribution P.
Okay, so it's like we're trying to get our best guess as close as possible to the real thing, even though we can't actually observe the real thing directly.
Exactly, yeah.
Okay, and then the paper goes on to talk about how they parameterize P to match the form of Q, and then they derive this NoProp objective function.
Right, so by matching the forms of P and Q, they make the calculations easier. And the NoProp objective function, it basically encourages each layer to predict a cleaner label that's consistent with the input data.
Okay, and the paper mentions this thing called the signal to noise ratio, or SNR, which is part of the objective function. What's that all about?
So the SNR, it measures how much noise there is in the label at each step, and the objective function uses that to kind of weight the contribution of each layer's denoising.
Okay, so it's like the layers that are dealing with more noise get to have a bigger impact on the overall learning process.
Yeah, that's a good intuition.
Okay, and then there are these continuous time versions of NoProp, NoProp CT, and NoProp FM.
Yeah, so these are variations on the basic no-prop idea. In the continuous time versions, instead of having these discrete denoising steps, you have this continuous process of noise diffusion and denoising.
Okay, so it's like you're smoothing out the process, making it more continuous.
Exactly, yeah.
And these continuous time versions, they have some interesting connections to other areas of research, like neural ODEs, right?
Yeah, absolutely. Neural ODEs have been a hot topic in deep learning lately, and NoProp CT and NoProp FM, they kind of bridge the gap between denoising score matching and neural ODEs.
Okay, that's pretty cool. So how does NoProp compare to other alternative learning methods like the forward algorithm and target propagation, which we talked about earlier?
So the key difference from forward is that NoProp doesn't need those two forward passes with the real and fake labels. It just has this one denoising objective for each layer.
Okay, so it's simpler in that sense.
Yeah, it's more straightforward.
And compared to target propagation, NoProp doesn't rely on learning those complex inverse mappings. It's more about learning to directly denoise the noisy label.
Exactly.
And the authors also emphasize that NoProp is really focused on this idea of back-propagation-free learning.
Yeah, they want to show that you can train these networks effectively without relying on backpropagation at all.
Okay, so that brings us to what I think is the most fascinating part of this whole paper, which is this idea that maybe we don't need representation learning as we currently understand it.
Yeah, that's a really profound implication of this work. So in most deep learning methods, the power comes from the network's ability to learn these hierarchical representations, these increasingly abstract features.
Right, like we were talking about before.
But NoProp is saying, well, maybe we don't need to learn those representations. Maybe we can just design them.
Just design them like handcraft them.
Yeah, basically. So in NoProp, the intermediate representations, they're not learned. They're just these fixed, noised versions of the target labels.
So the network isn't figuring out how to represent the data on its own. It's working within this predefined representational space.
Exactly. And the learning is all about mapping the input data to a cleaner version of that space.
Okay, that's a big shift in thinking. So what are the implications of that? Like why is this such a big deal?
Well, it challenges this core assumption in deep learning that the key to success is learning these really complex representations automatically.
Right? Like that's what makes deep learning so powerful.
Exactly. Yeah.
But NoProp is suggesting that maybe there's another way.
Right.
Maybe we can achieve similar or even better results by just being clever about how we design the representational space itself.
Exactly.
And that opens up a whole new world of possibilities, right? Like maybe we can design representational spaces that are more efficient or that are more robust to noise or that are better suited for specific tasks.
Yeah, absolutely. It's a whole new direction for research.
Okay, so let's talk about the actual results. Table 1 in the paper shows the quantitative performance of NoProp on those benchmark data sets. What are the key takeaways there?
So the results are really quite impressive. So the discrete time version of NoProp DT, it achieves accuracy on MNIST, CFAR 10, and CFAR 100. That's comparable to backpropagation. And in some cases, it's even a little bit better.
Really? So it's not just keeping up with backpropagation, it's actually beating it in some cases.
Yeah, on some of those benchmarks, it's actually slightly better.
That's pretty remarkable, and it's doing this without any forward propagation during training.
Right. Yeah, it's a completely different approach, and it's still getting really good results.
And the paper also mentions that NoProp has a much lower memory footprint, right?
Yeah. Yeah, Table 2 shows that NoProp uses significantly less GPU memory during training compared to backpropagation. And that's because it doesn't have to store all those intermediate activations for the gradient calculations.
Right,
So
right.
it's much more memory efficient.
Okay, and then there's this figure 2 in the paper that shows these visualizations of the learned class embeddings for NoProp DT.
Yeah, so those visualizations they're really interesting. They kind of give you a glimpse into how NoProp is representing the different classes. And what you see is that the initial random embeddings, they evolve during training to become more distinct and more characteristic of each class.
So it's like the network is learning these prototypes for each class, even though it's not learning hierarchical features in the traditional sense.
Exactly. Yeah, it's finding these representative examples within that predefined representational space.
Okay, so even though it's not doing representation learning in the same way as backpropagation, it's still learning some kind of meaningful representations.
Right. Yeah, it's a different kind of representation learning.
Okay, and then the paper also talks about the continuous time versions of NoProp, NoProc CT, and NoProp FM, and it looks like those generally perform a little bit worse than NoProp DT.
Yeah, that's right. The continuous time versions, they tend to have slightly lower accuracy than the discrete time version. And the authors speculate that that might be because of the added complexity of having to deal with this continuous time variable.
Right, right.
But even though they're not quite as accurate, they still outperform other methods that try to avoid backpropagation, like the avoidance sensitivity method, which is a common way to train neural ODEs.
Okay, so they're still competitive in that sense.
Yeah, and they're also more computationally efficient than a joint sensitivity.
Okay, and then there's this interesting observation about NoProp FM struggling with one hot encoded labels on CFAR 100.
Yes, so CFAR 100, it has 100 classes, and if you use one hot encoding to represent those classes, NoProp FM has trouble learning. But if you use learned embeddings instead, it performs much better.
Okay, so it's like the choice of representation even matters for NoProp.
Yeah, it's still important to think carefully about how you're representing the data.
Okay, and then finally the paper talks about this idea of a trainable noise schedule.
Yeah, so in the continuous time versions of NoProp, you can actually learn the noise schedule during training. So instead of having a fixed schedule for how you add noise to the labels, you can let the network figure out what the best schedule is.
Okay, so it's like the network is learning how to best corrupt the labels to make the learning process more effective.
Exactly, yeah.
That's pretty wild.
It is.
So, so to wrap things up, NoProp is a really exciting new approach to training deep neural networks. It's challenging some of those fundamental assumptions that we've held onto for so long.
Yeah, it's a real paradigm shift.
And it's showing really promising results. So what are the key takeaways here for our listeners?
Well, I think the biggest takeaway is that no prop is a viable alternative to back propagation. It's not just a theoretical curiosity. It's actually working well on real world tasks.
Right.
And it's offering some really interesting advantages like improved efficiency, lower memory usage, and potentially even better accuracy in some cases.
Okay, so it's not just about being different, it's about being better.
Right.
And the other big takeaway is this whole idea of designing representations instead of learning them.
Yeah, that's a really profound implication of this work, and it opens up a whole new set of research questions.
Right? Like how do we design these representational spaces effectively and what are the trade-offs involved?
Exactly. Yeah.
So we've covered a lot of ground today, but I think the most important question is what does this all mean for the future of deep learning? Like where do we go from here?
Well, that's the million-dollar question, right? But I think no prop is a sign that we're on the cusp of some really big changes in how we think about deep learning, and it's an exciting time to be in this field.
Absolutely. So for all you listeners out there who are interested in pushing the boundaries of artificial intelligence, I think this is a paper that you definitely want to check out. And maybe no prop will be the spark that ignites the next revolution in deep learning.
I think that's a great way to put it.
So until next time, keep exploring, keep questioning, and keep pushing the limits of what's possible.
And keep learning.